In this presentation, we will show how to use Excel to make an XY scatter plot. The particular example will be of Archimedes Principle, and we will include a linear fit to the data. While our emphasis is on Excel, making plots, fitting data, and then using that fit of the data, we will nevertheless explain the source of this data for context. An object is attached to a spring balance, a fancy term for a scale, and that object is lowered into a beaker that is filled with liquid, and that beaker has a spout. So the object is said to displace the liquid, spills out the liquid, as the object is lowered. And then we take a reading of the volume in the graduated cylinder, as well as a reading on the spring balance. The experiment resulted in the 4 data points seen on the left. Each data point consists of a volume and a tension. The volume is considered to be the independent variables, that the volume was controlled in the experiment by lowering the object. And it is the independent variable, and it will be displayed on the x-axis by convention. The tension is the dependent variables. After the object was lowered, then we see what tension happens to arise from it. And it will be, by convention, be displayed on the y-axis. So we will say that the tension depends on the volume displaced, or a related term is correlation. The tension is correlated with the volume displaced. We want to go beyond simply saying that when the tension goes down, the volume goes up. We want to make a sort of mathematically precise description of just how the tension goes down when the volume goes up. In addition, we want to visualize the results. We want to see it for our own eyes. So we're going to take our data points and represent them as a point on an xy plane, where the x, the horizontal axis, is going to represent the independent variable, for us, the volume, the displaced volume, and the y is going to represent the dependent variable, in our case, the tension. Then we're going to fit that data. We're going to make a mathematical function that has what are called variables and parameters. And in our variables are, again, our y and our x, the y being the tension and the x being the displaced volume. And then the parameters, in this case, in the case of a line, a slope and a y-intercept, are going to be chosen such that the data points are closest to our data. Then when we have this fitting result, we will be able to go beyond the data points that we actually measured. We just want to note here some overlapping terminology. This mathematical modeling of the data, in Excel, it'll be called a trendline. This is a term that comes more from the business world. In science, math, and statistics, we'll more often see the terms regression and fitting. Here we see the data entered into Excel. It was either typed in or copy-pasted from some other source. In column A, we see the independent variable, the x values, and in this example, the volume displaced. In column B, we see the dependent variable, or the y values, in this example, the tensions. We see that the column has a label. Cell A1 has words, volume displaced, along with the units of milliliters. All the numbers below it are simply just numbers, and you can tell that in Excel by the fact that they are right justified. Similarly for the tension column. Excel will become confused if you try to plot data points that it does not recognize as numbers. We highlight our data. It is optional whether you include the label or not in your highlighting. When you've highlighted the data, you will go to the Insert on the top menu and then go over to the Plotting region and choose a scatter plot. We're going to choose the option that has only data markers. We are going to later add a fit line, and we want the fit line to be the only line in the picture. Here is our result. As you can see, the horizontal x-axis has the volume values, and the vertical axis has the tension values. When the chart is highlighted, you will see chart-related items on the menu at the top. If the chart is not highlighted, you will not see these items. It is possible to add the features we want in our chart one by one, but it is far more efficient to go to Quick Layout and choose Quick Layout number 9. With the chart highlighted, go to Quick Layout, choose Layout number 9. It has many of the features we want in one efficient step. It includes axis labels. It will automatically add a linear trend line. It will display the equation and the so-called R-squared value. More on that later. The axis labels provided are generic axis labels, so we must provide the label relevant to our data. On the x-axis, we type volume displaced with the milliliter unit indicated, and on the y-axis the same, tension, and with the Newton unit indicated. Again, remember that the x-axis came first and was the independent variable and was the volume. The y-axis came second, was the dependent variable. In our case, it was the tension. I will refer to this chart as a plot of tension versus volume displaced. For instance, if I asked you to make this chart, I would say plot tension versus volume displaced. Many find this terminology confusing, since the name of the y dependent variable comes first. So if you say tension versus volume displaced, it's y versus x. The thing that comes first in the title is the y, and the second thing is the x, opposite of the way that you present the data to Excel. It might be useful to think of it as tension as a function of volume displaced, since the convention in mathematics is to have y as a function of x. I rarely make something like tension versus volume displaced the actual title of the graph. It is not wrong, but it does not convey any information not contained already in the axis labels, thus it's redundant. I will try to make the title something that adds additional information when I can. So I highlighted the title and changed it, but instead of calling it tension versus volume displaced or tension as a function of volume displaced, I entitled it Archimedes Experiment Data to convey some additional information, and that is that this data relates to the concept of Archimedes Principle in physics. In a simple graph like this with a few data points and a simple fit, I will often delete the legend by right-clicking on it and choosing the delete option. In graphing, the convention is that the data points are represented by markers, the blue dots here, and the fits are represented by lines or curves. There's nothing wrong with the legend, but since we're following the conventions and the data is relatively simple, it provides nothing additional, and so I considered it redundant. Layout number 9 provided us automatically with a linear trend line, but Excel can fit to other functions as well. If you wanted one of these other functions, you could right-click on the trend line, choose the Format Trend Line option, and then use the radio buttons on the side to choose one of the other functions that Excel knows. In the example we're dealing with, the line is the appropriate choice, and so we will keep the default choice. We can change the location that layout number 9 gave the displayed equation. Highlight the box and simply drag it to a new location. If you want to change the font size, highlight the text, go to the Home tab, and then use the drop-down list next to the font to choose a new size. If, as showed previously, you wanted to change the fit function, say to a polynomial, then you might find that after changing the font options, the displayed equation does not change, does not update to the new choice. In such a case, you would have to delete the display and then re-add it. So here we have our results, our XY scatter plot of our data, our visualization of our data, the blue data points, and the dashed blue line, fit line. It'll go a long way to our understanding of the fit line to recall that the Y's are tensions and come in newtons, and the X's are volumes and come in milliliters. And remember that the purpose of our modeling the data and getting the line is to move beyond just the 4 points that we originally started with. We've modeled the data by a straight line. A straight line has two parameters, a slope and a y-intercept. Here we will talk about the y-intercept. In our example, the 3.0632 is the y-intercept. It is a y, and thus in our case it is a tension and comes in units of newtons. The y-intercept is the value for y when x is 0. You can see this by putting x equals 0 into the equation. Thus, in our example, the y-intercept is the tension when the x, which is the volume displaced, is 0. In other words, it's the tension we would expect if the object were completely out of the liquid. So there would be 0 displacement. So if I ask the question, what is the y-intercept, you would tell me 3.0632 newtons. And if I asked you what the interpretation of the y-intercept is, you would say that it was the tension when there is no displaced volume. The other parameter in a straight line is the slope, the number that multiplies x. So if you're going to multiply a number by x, and x in our case comes in milliliters, and we are going to get a y, which in our case comes in newtons, then the units of the slope should be newtons per milliliter. The slope can be thought of as the rise over the run, or the change in y over the change in x. So again, its units are the y units divided by the x units, giving again newtons per milliliter. One way to talk about the slope is to say that it is the expected change in y if the x were to change by 1. And another way to talk about the slope is as a rate of change. So if I said, what is the value of the slope, you would give me the number and the units, negative 0.0126 newtons per milliliter. If I asked you the interpretation of the slope, you could say that if the volume were to increase by 1 milliliter, the tension would decrease by 0.0126 newtons. Or you could say that the rate of change of the tension with respect to the displaced volume is minus 0.0126 newtons per milliliter. We previously talked about the y-intercept. We can also talk about the x-intercept. Our standard equation is solved for y equals mx plus b. But we can also solve it for x. Divide through all terms by m, and subtract the b term minus b on m from both sides. Then the x-intercept will be the x value when the y is set equal to 0. As you can see from the equation above, that's minus b on m. And for our particular numbers here, that's going to be 243. This is the net value of an x, so it's a volume, and it has units of milliliters. In particular, it's the x, or the volume, that the object would have to displace in order for the tension to be 0. Now the object was shaped as a cylinder, but if it were shaped more like a boat, then this is the volume that would be under the liquid when the boat was floating, when the tension was 0. So here again on the left, we remind you of what the data was, and then the fit equation that came from that data. And the purpose of the fit equation was to be able to move beyond the 4 points that we had measured. The x values in the data range from 8.4 to 33.4 milliliters. If we use our fit data and use x's within this range of data, we are said to be interpolating. For example, we can make an estimate of what we think the tension would be if the volume displaced were 15 milliliters by putting 15 into the equation and getting about 2.87 newtons. The process known as extrapolation is when we try to go beyond the data in either direction of the data that we got the fit equation from. So again, the x values range from 8.4 to 33.4 milliliters. And so if we take an x value that is either less than 8.4 or greater than 33.4, we are extrapolating. So our estimate of a tension for a volume of 40 milliliters would be achieved by putting 40 as x into the equation, and we would get a tension, an expected tension of 2.55 newtons. The remaining quantity for us to discuss is the so-called R-squared value. We can see in the curve that it falls under the fit line. R-squared equals 0.9996. We will discuss this in more detail at a later time. But for now, R-squared close to 1 is an indication of a good fit. And so this is obviously a good fit. We can also see that by the fact that the model, the dashed line, goes very close to all of the large blue points, our data points. The R-squared value can be useful for comparing different fits. So if we were to choose other forms that Excel provided to compare them to see if any of the other forms were better than a line, we could compare their R-squared values and see which type of fit is the best.